Good morning. This is another experiment using an XSpice kit in the interfacing lab. We are going to study about working and responses of off-wave and full-wave rectifiers. What is a rectifier? In simple terms, rectifier is a circuit or device which converts an alternating current into a direct current. We are going to study two parts of wave as well as full-wave rectifiers. So basically, it's a study of rectification with and without filters in this interfacing lab. This is a circuit of half-wave rectifier. A diode, ordinary diode, is a unidirectional device. That means it passes current in only one direction and does not pass in the opposite direction. So when diode is connected in forward bias, it conducts. In reverse bias, it doesn't conduct. That's the basic principle. This is the circuit which can be constructed using an XSpice kit. So WG is a wave generator. Here we have chosen it as a sine wave. A1, A2 are the terminal to measure the input voltage as well as output voltage. A2 measures output voltage across load resistance RL with respect to ground. And this is a circuit without filter. So with filter also this behavior can be studied. So filters can be of any type, but here in this lab we choose only capacitor filter which is connected across load resistance RL, exactly like this. The output of off-wave rectifier is that in the case of off-wave rectifier, it removes the negative pulse and allows only positive pulse. Now because of that, you get an output signal like this. The dashed black colored line is an input signal. The continuous red line is an output signal. This is the actual output of an off-wave rectifier. Note that this red signal is below by a certain value from the output. So that value, if you measure exactly, that corresponds to 0.7 volt. Y-axis in this plot is voltage, x-axis in the plot is time. Note and understand that. So 0.7 volt actually finally corresponds to the band gap of the diode. So the output voltage because of that is lowered by a value of its band gap voltage by value of 0.7 in this particular case. So this is the off-wave rectifier output without any filter. Basically we wanted to have a DC signal exactly like that, having certain value, some slight value like this, but what we end up is getting a off pulse signal in the positive side and without any negative side signal. So this kind of signal is called as a pulsating DC. This pulsating DC contains many ripples. All those ripple factor we have to understand and we are going to estimate in this particular experiment. Now for a pure sinusoidal input, the ripple factor is defined as square root of Vrms by Vdc whole square minus 1. If you compute that analytically, it turns out to be 1.21. It's a dimensionless quantity. Vrms is root mean square voltage and Vdc is DC voltage. Now this, instead of that, we are more interested to understand the behavior of the circuit with the filter. So we are going to repeat the experiment for different capacitor filter where for values 1 microfarad, 4.7, 10 and 20 microfarad across RL, and we measure the output voltage to estimate the ripple factor. The expression for ripple factor with capacitor voltage is slightly different. So with capacitor filter, Vrms can be defined as equal to VRPP divided by 2 root 3. Now that expression is used here because the output with the capacitor filter almost resembles a triangular wave. So for a triangular wave, Vrms is defined with this expression. VRPP is a peak-to-peak ripple voltage. And the ripple factor with the filter is just a Vrms by Vdc. So you get this expression Vrms Vdc equals VRPP by 2 root 3 times Vdc. That's a ripple factor with capacitor filter. And theoretically also one can estimate ripple factor using this relation, which is equal to 1 by 2 root 3 f for RL in C. F4 is the ripple frequency, RL is the load resistance, and C is the capacitance of the capacitor used in the circuit. So using all this, actually one can estimate theoretical value of ripple factor, and experimentally one can measure ripple factor. Then they both can be compared to understand the working of the off-wave rectifier. This is the output of a off-wave rectifier with a capacitor filter of 4.7 microfarad filter. Again, dashed line is the input signal and the continuous red line is the output signal. This particular picture also shows how actually the different parameters are defined in the output voltage, output signal, from the output signal. Basically, you must concentrate mainly on this particular continuous red signal. So if you measure the time between two successive peaks, that gives the periodicity of the ripple signal, output signal, and reciprocal of that gives the frequency of the ripple signal. So that's an important thing that you should measure, and you are going to measure the value of voltage between this and this, positive peak to negative peak. That's actually ripple voltage, peak to peak voltage. So that you have to measure. Another two parameters what you are going to measure is the value from the 0 to the peak value of the ripple, which are called, which are denoted as VRP. So it is the important thing that will be used to measure VDC. VDC is actually the average of these two peaks, and that is equivalent to value from 0 to the DC value of this output. So this pulsating AC output is equal to produces a DC voltage which is denoted as VDC. So experimentally you are going to measure VRP, VRPP and VDC. However, in the calculation we don't use VP, we use only VRPP and VDC and frequency. And then full wave rectifier. In the case of full wave rectifier, negative pulse is converted into positive pulse. In order to do that, what we use WG bar, which is exactly 180 degree out of phase with the input signal WG, and these two signals are synchronized inside the XSPICE kit. So when WG is positive, WG bar will be negative. That's how actually it works. So when WG is positive, diode D1 conducts, and diode WG will be negative, therefore diode D2 will not conduct. Similarly, when WG is negative, D1 will not conduct, and at the same time WG bar will be positive and D2 conducts. So you get output across A3, which is measured across load resistance. That's how actually a full wave rectifier works here. A capacitor filter can be connected across RL. In fact, you can connect many capacitors, say value from 1 microfarad, 4.7, 10, 20, 4700. You can construct any value, and whatever value you connect should be like that. It should not distort the input signal. So for pure sinusoidal input, the ripple factor for full wave rectifier is found also to be 0.483. The expression for ripple factor is already given in the previous slide. I repeat all those steps which are mentioned in the off-wave rectifier for the full wave rectifier and report the thing. So in this actually, there is one difference between theoretical value of ripple factor. A factor of 1 by 2 is there, extra is there in the for full wave rectifier, and for full wave rectifier ripple frequency is twice the input frequency, so that you will understand when I show the output of the full wave rectifier. So this is the actual working of full wave rectifier without any filter. There are three curves here. Black dashed curve is one input signal, a red dashed curve is another input signal, green continuous curve in this picture is actually output signal. Notice that when one of the input is positive peak, then at the same moment the second input signal will be negative. Therefore, in this case, one of the diode conducts, another diode will not conduct. So this will reverse when it's exactly at 180 degree apart. When the second signal is positive, the first signal will be negative. So in this case, this diode will conduct and this diode will not conduct. In both the cases, what happens? The output signal will be there, unless like the half-wave rectifier. So you have both output for both for negative as well as output false. So in other words, if you just concentrate only on this negative, only black color dashed line, when this is positive, you get a output here. When this black color line is negative, then also you get a output. So in this sense, the output of the full wave rectifier is twice the frequency that of the input signal. So this is actually full wave rectifier with a 10 microfarad filter. You can notice that in earlier, for the case of half rectifier, I showed you one with 4.7 microfarad filter. For full wave rectifier, this diagram shows with a filter of 10 microfarad capacitor. So you can notice that the value of this ripple decreases with increase in capacitance value. In effect, that also increases the effective DC of the output. So this is how actually full wave rectifier output measure. For all the cases, you have to measure many quantities, both for half wave rectifier and full wave rectifier. These are the things that you should notice. For in case of full wave rectifier, this factor 4 will be there instead of 2. For half wave rectifier, it will be just 1 by 2 times root 3 f of r RLC. For full wave rectifier, instead of 2, there will be 4. So this is the tabular column to note down all the parameters and finally to estimate ripple factor experimentally and ripple factor theoretically. So if the two are working properly, then the two values should match, and you can make an error table between theoretical and experimental values. So that's the procedure for half wave and full wave rectifier, and that ends the lecture.